This is going to be the best unit ever because it's the last. Okay? And we will be finishing this unit on Friday. Chi-squared goodness of fit test. So this is one of 3 chi-squared tests. This is the chi-squared goodness of fit test. Some people call it the chi-square Goff test. If you have taken AP biology, you have done this before. Wow. All right, so here we go. Here's the example we're going to use. The M&M's Mars companies states that on their website that on average the mix of colors of M&M's milk chocolate candies will contain 13% each of brown and red, 13% of brown and red, 14% yellow, 16% green, and 20% orange, and of course there's 24% of those wonderful blue raspberry M&Ms because they taste like raspberries. So 24% are the blue ones. Those are the color distributions that they state should be in all of the M&Ms across America. So you go and you get a bag of M&Ms. And you open the M&Ms, and here you have a one-way table. This is a one-way table because it's literally just one row of information, and it's just giving us a count or a number of the colors. So you open this bag of M&Ms, and you find a total of 60 M&Ms in your bag. In that 60, you have 9 blues, 8 orange, 12 green, 15 yellow, 10 red, and 6 browns. So here's the question. Does your bag of M&Ms contain the correct color distribution that M&Ms says that it should? So here's one way you could do it. We could test each color individually using a one-prop z-test. Here's how that would look, you guys. I would look at the blues, and I would say, well, blue is supposed to be 24%, and I got 9 out of 60, and so do I have convincing evidence that blue is wrong? I would need to do a full state plan do conclude for blue. Then I would move on to orange, and I would say orange is supposed to have 20%, and I would do a full state plan do conclude to see if that is, in fact, correct. And then I would do one for green, and one for yellow, and one for red, and one for brown. Would you guys like to do 6 state plan do concludes today?
No.
Oh, but why not? Yeah, me either. So look, that would be stupid. Let's just be honest. That would be stupid. And there's some big problems that would occur with this. First of all, it's stupid. It's time consuming. That would be very time consuming. Ain't nobody got time for 6 state plan do concludes just to see if these M&Ms are correct. Okay? Here's the other problem, you guys.
Dude, that's what I'm saying.
The other problem is what if the blues turn out to be correctly distributed, the oranges turn out to be correctly distributed, the greens are wrong, the yellows are wrong, the reds are good, and the browns are wrong? Then is the distribution overall correct, or is the distribution overall wrong? So we would have conflicting information. We would have conflicting results. Some of them would be correct, some of them would be wrong, and we would have a conflicting result. So that would be a problem. So here's what we're going to do. We're going to use a new test. There's a new test in town. It's called the chi-squared goodness of fit test, and it's going to test all of them at one time. One state plan do conclude. Yay. Aren't you excited, you guys? Just one, not 6. That's too many. Okay. All right, so that's what we're going to do. But before we do that, I got to tell you guys a few things about how this works, okay? The chi-square statistic. So the chi-square test statistic is similar to a z test statistic or a t test statistic, okay? So we're going to have a null hypothesis. Now, our null hypothesis is going to look slightly different than what we've been doing before. We're not going to say that chi-squared equals anything, okay? We're not going to say that. What we are going to say, our null hypothesis would be this, that the claimed distribution is correct. We're going to give the M&M company the benefit of the doubt that they are not lying to us, because honestly, why would they, right? Why would they lie to us about the color distribution of the M&Ms? Why? So that's one way you might see it. Now, there is a more detailed way that you could do this. You could say that the null hypothesis is that P B, like that would be for blue, equals blank, and then like PO equals blank, and then P like R for red equals blank, and then PBR for brown equals blank. Like, okay, you could do that if you wanted to. You could list out each individual one. So again, saying that's the company's claim. Either one of those is absolutely correct, and you could use either one. I usually go with the easy one. The claim distribution is correct, right? All right. The alternative hypothesis. Any guesses what the alternative hypothesis would be? Oh, man, you guys. You've been doing this so long. That would be that the claimed distribution is incorrect or not correct. Either one, same thing. Now, if you wanted to do the specifics, then you could do this. You could say your alternative is that P sub B for blue does not equal blank, or, notice there's an or, P sub O for orange does not equal blank, or P sub R does not equal blank, and so on and so forth. What that one is saying is that it doesn't matter which one, but you are thinking that one of them is wrong, or at least one of them is wrong. That's how you do a null and an alternative hypothesis. Null hypothesis, the claim is correct. Alternative, the claim is wrong. Cool? Cool. Okay, back to our situation here. And what are we looking for? In a chi-squared goodness of fit test, here's what we're looking for. We compare observed counts to expected counts to see if a difference is noted. We compare our observed counts to our expected counts to see if a difference is noted. And we're looking to see if the overall distribution is correct or not. Okay? We are testing to see if the overall distribution is correct. Okay, so here's our data again. Our colors are in the first column. The observed number of M&Ms with that color that's in this hypothetical bag is in the second column. The claimed percentage from the company is in the third column. So what we need to do is we need to find out what should we have gotten? What is the expected number of each color? So there were 60 total M&Ms in the bag. For blue, we're going to look at blue first. 24% of the M&Ms should be blue. So if I've got 60 M&Ms in the bag and 24% of them are supposed to be blue, How many blues should I have gotten? So we need to find out what is 24% of 60. Do you guys know how to find 24% of 60? Please say yes. Yes, ma'am. Yes. Yes. 0.24 times 60, which is 14.4. We should have gotten 14.4 blue M&Ms. But guys, we didn't. We only got 9. Now, here's the question. Is that different because blue's distribution value is wrong, or is that different because of sampling variability? Okay? Orange was supposed to have 20%, and I only got 8 out of 60 that were orange. How many orange candies should we have gotten? 12. 20% of 60 is 12. We should have gotten 12, but we only got 8. All right, green. We should have gotten 16% green. We got 12. What is 16% of 60? 9.6. We were supposed to get 9.6 green M&Ms. We got 12. We got more greens than we were supposed to. All right. 14% were supposed to be yellow. What is 14% of 60? 8.4. We were supposed to get 8.4. We got 15. We got more yellows than we were supposed to. Red and brown were both supposed to be 13%. What is 13% of 60? 7.8. And we got 10 reds and 6 browns. Okay, now, here's the deal, you guys. All right? Are these far enough apart that you would disagree with their claim, with their percentage distributions? But what's the standard deviation? Well, we don't really have one. With chi-squared, there's not a standard deviation that's associated with it. But what is associated with it is this column here. This is the chi-squared contribution. This is how we're going to find out the standardized difference. So this is kind of like our T or our Z. So this is going to give us a standardized difference from what it actually was supposed to be. Now look, the way you do this is you take the observed value, you subtract the expected value, and then you square that. Then you divide by the expected value for that particular color. That's how you get this standardized distance that they are away from each other. If my observed value and my expected value are the same, let's say I had 10 of one color and I was supposed to get 10 of that color. What would this be? What is 10 minus 10? 0. What is 0 squared? 0. And 0 divided by anything is 0. If my observed and my expected are exactly what they're supposed to be, and I get exactly what I'm supposed to get, then I would get a chi-squared contribution of 0, meaning I'm exactly where I'm supposed to be. The chi-squared contribution, as it gets bigger, I'm getting further away from what I'm supposed to have. All right? So these numbers, I want them to be small. These are my standardized values that tell me how far away I am from what I'm supposed to have. All right? So we're going to calculate these real quick. So for blue, for example, we need to take 9, which was the observed amount, subtract the expected amount, square that. The reason we square it is we get rid of the negatives. And then we're going to divide by that expected value. This is going to give us the standardized distance between what we should have gotten and what we actually got for the blue M&Ms. What did you guys get?
I got 2.025.
That is exactly right. 2.025. That means that we got 2.025 standard units different for blue than we should have. Okay? The next one would be orange. We would take 8, we would subtract 12, We would square that, and we would divide by 12. This is going to be the standardized distance that the orange candies were away from what they were supposed to be. What'd you get? 1.3 repeating. Beautiful. All right, go ahead and calculate the rest of those. Write them down. I'll give you the answers in a minute. Maybe. Maybe I'll make you do. Maybe I'll randomly call on people to tell me what they are. Wouldn't that be fun? Look at this kid. All right. I'll randomly call on Matthew. No, I'm kidding.
No.
Nothing? All right, guys. What is the chi-square contribution or the standardized distance for green? 0.6. Just 0.6? Yeah. Okay, cool. All right, what is the standardized chi-square contribution or distance for yellow? 5.186. Holy moly. All right, what is the chi-square contribution or the standardized distance from what it should have been for red? And for brown? Beautiful. Okay, so looking at these numbers, which color was the furthest away from what it should have been? Yellow. Yellow was 5.186 standard units away from what it should have been. This standardizes everything. All right, so yellow is a big problem. Which color was the closest to what it should have been? Brown. Okay, cool. Brown was pretty close. All right. So how do we know if we have good evidence that the claim distribution is incorrect? All right. So when the chi-square contribution, which that's what we just found, when the chi-squared contribution is large, we have good evidence against the null hypothesis and for the alternative that something in the distribution is wrong. Something is off. Now, obviously, we can tell that yellow is off, all right? But is it off by enough that we would say the whole distribution is wrong? So here's what we're going to do next. We're going to add all of these chi-squared contributions up. We're going to add all these up. Now, in a perfect world, you guys, in a perfect world, when we get every single color exactly what it should be, then my chi-squared contribution, when I add all these numbers up, I end up with 0. That means that there's no difference at all. I got exactly what I was supposed to every single time for every single color. So in a very, very, very perfect world, which does not exist, I apologize for that PSA that I just gave you, but these would all be zeros because those observed and expected numbers would be exactly the same every time. And all of these would add up to 0. The further this number is from 0, the bigger the difference is between the overall distribution being correct. So add all those guys up, and I believe you get 10 point something. What'd you get? 10 point?
10.177.
10.177. 10.177. Okay. Here's the final question that we need to answer. Is that far enough away from 0 that I would say that this distribution is wrong? Yes? Adam thinks yes. Anyone else think yes? Yeah? 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 Yeah. That's pretty, 10 standard units away? Well, let's just see about that. Adam's now nervous. Don't be nervous, Adam.
You could just say yes and
I could
be done.
and be done. And we could just call it a day.
Yeah.
Wouldn't that be great? Yeah, but that's not going to happen. All right, so here's a distribution. Here is a chart or a visual that shows your observed and expected counts next to each other, okay? Now look, we see some fairly large differences between the observed and expected counts. Obviously with yellow specifically and blue, those are pretty big differences. Here's the question, you guys. How likely is it that differences this large or larger, as extreme or more extreme, would occur just by chance? This question is asking us to find the p-value. You guys, I'm so excited. We still get to find p-values. Woo! Let's go. To answer this question, we're going to calculate the test statistic that measures how far apart the observed and expected counts are. We actually already did this, you guys. And that test statistic is the chi-squared statistic. Chi-squared is like T and Z. Z is for proportions, T is for means. They tell us how far we are from what we should be if the null is correct. Chi-squared is going to tell us how far we are from what we should be if the distribution is correct. We already know we're 10.1 whatever it was, 10 standard units away. Adam, and many of you agreed with him, think that that's too far. Okay, we're going to find out in just a minute if that is really too far. Here's how you get it. Chi-squared is the summation. We actually just already found this. It's the summation of the observed minus the expected squared divided by the expected. We already did that. We did that in the chart a minute ago. And when we did that, we added up all of those chi-squared contributions, all those little numbers, and we got 10.177. This is our chi-squared test statistic for this problem. The only thing left to do is find the p-value. So I need to find the area as extreme or more extreme than 10.177. Plot twist, you guys. Are you ready for a plot twist? Do you guys love plot twist? It's like the end of the movie. You think you know what's going to happen, and then boom, in comes somebody you didn't even know was in the movie. Chi-squared is not a normal distribution. Oh my gosh. What are we going to do? No, we're not going to give up, you guys. We're not going to give up. We're going to continue, and we're going to figure this out. I'm so excited. Oh, I said this, but I forgot. We didn't write it down. What does the value of the chi-squared test statistic indicate? All right, chi-squared is how far in standard units are observed values are from the expected values. Just like the T and the Z test statistic, okay? Chi-squared is like Z, that's for proportions, and T, which is for means. The difference here is that Z and T work for a single or for two populations, comparing two distributions, two different populations. Chi-squared works for a whole distribution. So I can test a whole distribution at one time. All right, so here it is, the shape. What is the shape of the chi-square distribution? It is not normal. It is a right-skewed distribution. Oh my. What in the heck are we going to do with a right-skewed distribution? I'm pretty sure we don't have a right-skewed CDF. Oh, but do we? Right-skewed. Why is it right-skewed, first of all? Why is it that I would only have a right-skewed distribution? In a perfect world where our expected values match our observed values, what is the chi-squared statistic? It's 0. And then thinking about the formula where you take observed minus expected squared and divide by the expected value, what kind of numbers are you always going to get? Always going to get positive numbers. So a chi-square statistic starts at 0. That's where the perfect world is. And it only goes off to the right. You're going to have a lot of little differences. This is sampling variability right here. There's sampling variability right here. But once we start getting over here, we have pretty well proven that we have the alternative hypothesis correct. And then here's the big question is how far is that? How far is the sampling variability going to account for? Is it 10.1 or is it only like 1 or 2? Okay. All right, so just a little note right here. Since we square observed minus expected, chi-squared cannot be negative. If you get a chi-squared test statistic that's negative, something went real wrong, like real wrong. Okay. Drum roll. We're about to get the p-value, you guys. We're about to find out if this distribution is right or not. We're about to be able to say if Adam is smart or stupid. Let's do it! Adam, I love you. All right. Look, here's some distribution, some chi-square distributions. There's some different chi-square distributions, you guys. Each chi-square distribution is different based on its degrees of freedom. Degrees of freedom is categories minus 1. It's kind of like n minus 1, okay? But we're going to look at how many categories there are. There were 6 different colors. So we have 6 categories minus 1. We have 5 degrees of freedom. If you guys look at this chi-squared distribution chart here, so the red one, I know it's not red on yours, but it's red on mine. But the red one is degrees of freedom of 4. That one, it's higher, and it allows for less sampling variability than when you have more categories. When you have more categories, you have a better amount of sampling variability available. That's why it changes. All right, we computed the chi-squared test statistic to be 10.177. Before we can find the p-value, we need to make sure our large count condition is met. This is not the normal condition because it's not a normal distribution. We're going to make sure the large count condition is met. So the large count condition for chi-squared distributions is all expected counts have to be greater than or equal to 5. All expected counts have to be greater than or equal to 5. So if you look back at the chart where all of our expected counts were all of those numbers bigger than 5? Okay, perfect. So we're good to go, you guys. We can now find the p-value. Let's do it. To find the p-value, you are going to use a calculator command called chi-squared CDF. Chi-squared CDF. It is found in the same place as normal CDF, TCDF, inverse norm, all of those things. So let's go to second vars. Second vars. And we're looking for chi-squared CDF. I believe it's number 8. Chi-squared CDF. When you go there, it's asking you what's the lower boundary. Your lower boundary is always your chi-squared number. So that would be 10.177. Your upper boundary is always infinity, because we're always going from the chi-squared value out to the tail. So all the way to infinity. So that would be 1 little e 99. Our degrees of freedom were categories -1. There were 6 colors, -1, so that's a degree of freedom of 5. There's our p-value. 0.0704. 0.07. We'll just go with 0.07. All right, so here's our p-value. We did chi-squared CDF. Our lower was 10.177. That's the chi-squared value. Our upper was infinity. It always goes to infinity. And our degrees of freedom were as 6 minus 1, which is 5. And we got 0.07. All right, you guys, what would we conclude? Well, the p-value is 0.07. How does that relate to the alpha value that we usually use? That is greater than the alpha value of 0.05. And so if the p-value is not lower than alpha, what would we do? We're going to fail to reject the null hypothesis, and that is because there is not convincing evidence that the distribution claimed is incorrect. AKA, here's what I just said. I basically just said that the difference in our M&M's candy bag was just due to sampling variability. And Adam is not stupid. He's really smart. Adam was just thinking of an alpha value of 10%, not 5. That's all. You guys, you just got to be on Adam's level. All right, you guys. Now, tomorrow, I'm going to show you how to do all of that in the calculator. But faster. Oh, don't you hate when I do that?